Good morning, everyone, and welcome to Algorithms and Data Structures. Today, we will continue with the lecture on trees. We've discussed trees last time, particularly we've looked into binary trees and how we can implement them and how we can traverse them. And we've implemented various algorithms. There's also some coursework for you to do, which are problems 12.1 to up to problems 12.3 you can do already. And today we will continue with trees. And first of all, I want to discuss with you more advanced search trees. And I'll show you soon why that's actually important. Search trees, we've seen binary search trees, and they are search trees because they are sorted, so I can search in them very efficiently. And when we have them, something can go wrong. And I will show you this now on the whiteboard. Something that can happen is the following. Imagine you're adding value 1 to a tree, and that's the root. Now, we add value 2, so we create a branch to the right, or as the right child of the root. If I want to add a 3, I would add the 3 as the right child of the 2. And then I add a 4, which I also add to as a right child of the 3. Do you notice what's happening here with this tree if I keep adding values that are sorted, for example, or that always the next value is greater than the one before, or the one that is coming is less than the one before? Do you start to see some pattern? If you see some pattern, maybe thumbs up. And one comment here is that we actually don't get a tree, we get more sort of a linked list. Yes, that's true. What's happening then if I want to search in this so-called tree? What impact will this have on complexity, for example? I'll see if there is some more insights in the chat. This will be O of n, yes, because I don't really have a tree, I have a linked list. And if I have a tree that is a binary search tree, but if it looks something like this, so for example, if I have value 4 in here, there a 2, the 1 and the 3, and then the 5 here, 6 and 7. If I have a tree where I try to keep it short, I'll say the term very soon, what to call such a tree here. If I try to keep it short and try always to use a left and a right child, what would be a search in such a tree like here? If you have a guess, send this to the chat. I'll see. Didn't see anything in the chat yet. Now there is. This is O of log of n. We'll later look at why. And here, this would be O of n. So we rather prefer the left tree than the right tree. The right tree is something that is sometimes called in the literature degenerated. One can wonder if the term is so good or not, but this is what this tree that is actually now a list, is sometimes called. And the left tree, in which I said we try to keep it as short as possible and add elements always to the left and right. This is called a balanced search tree. And a balanced search tree has the big advantage that I can really take advantage of this tree structure and I can search in it very efficiently. Adding values and removing values will probably be a bit more complex in a balanced search tree than if I don't enforce that property. But oftentimes I store data and then I spend far more requests on searching than updating. That's why maybe such a balanced structure is actually quite useful. So, and with the trees we have implemented so far, we would rather run into a degenerated case, and the order in which I'm adding these values really matters. If I say I have the values 1 to 7, and I was adding them just from 1 to 7, then I would get the right tree that is degenerated. But if I started, say, for example, with the 4, and then the 2, then the 1 and 3, then the 6, 5, 7, then I would actually get such a balanced tree. So the order in which I'm adding my values has impact on the structure of our trees so far. And that's maybe not too great, and we want to improve on that. And that's why we are now interested in balanced search trees. And if you look in, say, most algorithms and data structures course, a lot of time is spent on balanced search trees and how to implement them. Now, in this course, I only discussed them very briefly, and there are a few reasons for that. First of all, we only have 90 minutes per week for the lectures, so we're somewhat limited by the total content we can do during the term, which is approximately 15 weeks. If we had like 180 minutes per week, I'd be more than happy to discuss this in detail. But most of you who are taking this course are actually studying computers, are not just studying general computer science, but cybersecurity or AI. And actually, a large majority comes from AI. So I feel we will rather do something in this chapter that is maybe a bit more linked to AI, which also will prove to be super helpful to the cybersecurity students, by the way. And this will be decision trees. We'll see this very soon. And that's why I just keep these balanced search trees very, very short, because they would probably be more of interest if you studied general computer science. And if you ever need them as an AI expert or a cybersecurity expert, you would anyway just be using a library in which they are implemented very well. Because I've introduced trees, and now if we do advanced search trees or balanced search trees, probably this just looks like an end in itself, like a self-purpose. And I rather want to use the trees in this chapter, given the limited time we have per week, to discuss more like an application of trees. But before we come to that application, which is decision tree learning, we will briefly look a little bit at binary search trees and what the idea is. There's a huge number of such trees available, for example, AVL trees, red-black trees. Then there are, for example, 2, 3, 4 trees. Sometimes they're called 2, 4 trees, in which a node can have up to 4 children, for example. So not just 2. And then there are B trees and a huge variation of B trees, which are probably the most complex ones from the ones I've mentioned here. And the idea is, what they are doing is, if you have your imbalanced tree and you keep adding values, it would probably be more and more imbalanced, and you want to conquer the imbalance by rotating the tree. This is something, if it's not relevant to the exam in this course, how to rotate a tree and how to implement it. But if you're curious about such a rotation, so do you see how to rotate around one node in order to restore a balance. This is also explained perfectly fine in the Goodrich book. And for example, if we have a degenerated tree that looks something like this, we could do a single rotation, and then we have B actually as the new root. And we have to reorder also the entries, which are here T1 to T4. And then I have a balanced tree. How to implement all of this isn't that difficult, at least for such binary trees. If you have B trees, it gets more complex because you not only need to look at that when you insert values, but also if you remove or update values, because then you may have to reorder the tree in order for it to remain balanced. But as I said, this isn't too important in the framework of this course. I wish we had more time to do it, but I rather want to discuss now something with you that is more applied. There's also an example of 2, 3, 4 trees, red-black trees. Red-black means some nodes are considered black while the others are considered red. Here, just for the visualization in a book, they are in white and black, but they are red-black trees in the literature. And given if a node is red or black, it has some other properties also when it comes to balancing this tree. We see this tree is not perfectly balanced. Typically, those trees don't require perfect balancing, which may be even impossible if you have, say, the wrong number of nodes in your tree for it to be perfectly balanced, but you want it almost balanced. And if you are beyond a certain threshold, then the tree may rebalance. But that's it so far about advanced types of trees or balanced search trees. We will now look into an application of all of this that you will find super helpful if you do AI, as well as if you do cybersecurity, because cybersecurity is also more and more driven now by artificial intelligence. We will look at decision trees. And decision trees are simple and successful forms of decision making. And a decision tree can actually be also seen as a set of rules eventually. And a decision tree could be something like this. I have a root, the root is A, and that's a variable I'm looking at my data set. And if A has the value no, so it's binary values, then I return value 2. Otherwise, if A is positive, so no means negative and yes means positive, then I still need to check B. And if B is yes, then I return 1. Otherwise, I return 2. So these boxes here, they are the leaves of the tree, and these are the classes. Here I would have a classification problem based on values in A and B. I would return class 1 or 2. Actually, this is just a decision tree for the AND function. So 1 would actually mean true, and 2 would mean false, because if A and B are true, I return, or if they're yes, I return 1. And if one of them at least is no, then I'm returning 2. You could also represent the OR function if you wish, or you can come up with more complex decision trees, like in a computer game. You want to know if an enemy is visible, and if this is not the case, you would check if the enemy is audible, and if that's the case, you would creep. However, if the enemy is visible and less than 10 meters away, you would attack. If the enemy is further away, you would have further nodes to check, and you would make a decision. Now, such decision trees as the ones you see here, they may be handcrafted, that some domain expert has actually set up these rules and built a tree. And eventually, each possible path from the root to a concrete leaf is like a set of rules. Like if the enemy is visible and the enemy is more than 10 meters away, and if the enemy is on flank, then I would move, and so forth. So you could eventually each path from the root to every possible leaf, you could just consider this to be a rule. So actually, it is just a huge rule set. But decision trees are very helpful because you can visualize them. So they are not a black box decision-making tool. If you, for example, look at other machine learning algorithms like a neural network is something that we call a black box by nature in most cases, because it makes decisions, maybe very good ones, but I don't know really why. And then I need to spend more time on making them explainable. However, a decision tree is inherently explainable because I can just print it. And then I can see why a decision was made. And decision trees, they can be used for classification. So this one here would be a classification tree. The concrete predictions I'm making can be class creeping, attack, or move. So there are three possible label values for my target, creep, attack, or move. I could have decision trees that only make binary decisions. Here I have three possible values. I could also have decision trees for a regression. So a regression would mean the label value is not discrete like here, but continuous like a real number. There are decision trees like this. But today, we will only look at decision trees for classification. Concretely, we will largely care about classification trees that just make binary decisions like yes or no, or one class or the other. And as I said, the output, so the target, is either discrete or continuous, so a classification or a regression. And the same distinction needs to be made for the input value. So the values in the variables I'm considering, these values can be just true or false. They can be from some other set. They could be from more than two possible values. If you have a finite number of possible values in your variables, like 5 possible values, for example, then we talk about a set. However, there are other decision trees that look at numeric values. And for example, you would then have, like this is still, say, binary if the enemy is less than 10 meters away, yes or not. But you could imagine that a decision tree splits this maybe in this node into multiple intervals, and based on the interval values, you would go to a different child node. So there could be more than two child nodes. These are all possible input data a decision tree could be dealing with, but we will now just keep it very simple. We will care about output values that are a class, concretely a binary classification, one label or the other. And we will care largely about Boolean input values. What we are doing could also be applied actually to set inputs, that we have more than two possible values in a label, but we don't care about the numeric ones, because we're just looking at the most simple decision trees. And the goal of today is that we're not handcrafting them, but rather we are learning a sort of or almost optimal decision tree purely from data rather than handcrafting a tree. Decision trees, they may look very simple, but in fact, it turns out they are extremely useful machine learning algorithms, or at least when I learned decision trees, because decision trees are very fast to be evaluated. They are explainable, and overall, they can make relatively good decisions, especially if you add some tricks. Now, how do I find a really good decision tree? Say I have a huge data set and I want to classify this data set correctly. So I want to learn for this data set a decision tree that would allow me to learn this pattern. I could try to handcraft a tree, but maybe that's not too great if it's a complex pattern and a huge data set. So I want to learn it. Now, there is an optimal decision tree for such a problem. An optimal decision tree here would mean the smallest decision tree possible that learns this pattern correctly. So I don't care here about uncertainty and that I'm, you know, making maybe wrong decisions. I want to perfectly learn the pattern in the data set with the smallest tree possible. And that would be the optimal decision tree. However, finding the optimal decision tree is NP complete, because there's a huge number of possible trees. And if I only care about binary trees, so binary decision trees, meaning my values in the inputs are binary values, as well as the label I'm trying to predict is binary, and I have n many examples, then in fact there are 2 to the 2 to the n many possible trees that I could come up with. And if n is just 10, then you would have here 2 to the 10, which is 1024, and then 2 to the 1024 is an unimaginably large number. So this really doesn't scale. I cannot just, you know, try to build every possible tree once n just gets a little bit larger than 2 or 3. And that's why I cannot just try out all possible trees and then pick the optimal one. Rather, I need some heuristic to find a good approximate solution of the optimal decision tree. So this is now an approximation algorithm, will not necessarily give me the optimal decision tree, but it can be shown that we typically get quite a good solution of the problem, and a relatively small tree for the problem, and we can actually learn it very, very quickly. What I want to do is now, we have this data set here, and the data set, as for example, from a computer game, we have 12 examples, and we have 3 input variables. One is enemy visible. Later, we will just call this visible to keep it short. So is the enemy visible for us? Yes or no? So no or yes. Then we have our 12 training examples, and they're always called X, and I put a superscript index. So this is the first one, this is the second one, and so forth. Then the enemy has a certain distance, and here I have 3 possible values: less than 10, 10 to 20, or greater than 20. And then the enemy is either armed or not. And based on these 3 input values, I have a label whether I want to attack or not. So yes or no. And this one here is the label, so the decision I want to be making. And I want to learn a decision tree for something like this. It's a relatively simple learning problem. We just have a few data points, but the advantage here is that this is something we can now try to learn together and write it out step by step and see how decision tree learning works. And we will get a tree that is fully explainable. So this will be far better understandable eventually when I make predictions than if I use a neural network. And if I used a neural network for a data set like this, I would anyway overfit and not be able to generalize. Has any one of you ever done decision tree learning? I know you're in your first year of the undergrad, or most of you, but I'm curious if any of you has ever done decision tree learning. If you have, maybe thumbs up or thumbs down. I only see no's, so that's good. So there's something new for all of you today. Probably the simplest decision tree learning algorithm, or one of the simplest ones, is ID3. And ID3 is an algorithm that also applies a divide and conquer strategy. In fact, if I have a data set like this, I don't know how to start. I need to pick one of those 3 attributes or input variables as the root, because either I decide from visible, distance, or armed, and then maybe I can directly pick the label, or maybe based on the input value, I need to look at one of the other 2 attributes. So what I'm doing is a divide and conquer strategy, because I first pick one attribute And from there, I continue the learning. And in fact, this is a so-called greedy divide and conquer algorithm. Greedy means the algorithm here would pick the biggest or most important attribute first. So one of those three attributes is maybe the most important one for making this decision. And this is the one I would pick as the root and then continue from there. So we are applying a greedy divide and conquer strategy. You're wondering, how do I determine the most important one? This is something we'll be seeing very soon. And this ID3 algorithm utilizes the entropy theory, which I'll introduce very quickly, or at least the key essence, in order to determine which one, or how to determine the most important attribute. This is the algorithm. I know it looks complex, but I'll go it through now with you, and I'll show you how it works. First, we discuss the pseudocode algorithm. Then we will go through an example together, and I'll calculate the numbers for you. And we'll start with the algorithm now. So the function is called decision tree learning. And I have a number of examples that I want to look at. So the examples are this one here, these 12 rows. I also have a set of attributes. So I have my attributes visible, distance, or armed. And I'm passing the attribute, the examples, and also the set of attributes. Initially, it's the set of all attributes, those three in this case. And I also have another parameter that is called parent examples. But this one doesn't matter for now yet. We will see it later, because this algorithm is actually a recursive algorithm. And then we have a couple of cases to abort. Imagine all examples have the same class. So I had my 12 examples from before, and imagine if they all had the same label, say all were true or all were false, then I would just pick that label as the classification, because then I don't need to do any learning. It could happen that I don't have any attributes left. This will happen maybe later when we do the recursive calls, because when we do recursion, we will always look at less and less attributes. And then it could happen that maybe I don't have any attributes left, say the attributes were those three input values, and maybe they are just not enough to fully classify yet. Then I need to make some exceptional choice we'll look at later. And through recursion, it could also happen that the number of examples that I'm running out of examples. But this is also something we'll be seeing later. So the first and the third condition are something more rare that may happen because of the recursion. The same holds true for number 2, the else if, which could also happen because of recursion. And actually, this is something that we'll rely quite a lot on, but it could also happen just by the data set I'm feeding in. All the examples have the same class, then I don't need to do any learning. Then comes the interesting part. Who of you is familiar with a notation that is called argmax? If you have ever seen an argmax operator, maybe thumbs up. If you have no clue what an argmax could be, maybe send this in the chat, or maybe if you know what an argmax is, thumbs up. If you have never seen an argmax, thumbs down. Good. Some have seen it, some have not. Then I'll show you this. Argmax operator is, imagine we have a function that is called f of x, and it will return values 1, 2, 3. 1 if x is 5, 2 if x is 10, and for x equals 1, it will return value 3. So this is our f of x. Before we get to the argmax, we'll get to the max operator. That is something you're definitely familiar with. The max operator. So I want to maximize f of x for x in my possible values. So the possible input values are 1, 5, and 10. And I want to maximize the function f of x for these possible input values. What would be the maximum value f of x or f can return for one of these, or for all these x I can put in? Maybe just share this in a chat. If you see what the maximum value is, and this is correct, it's 3, because 3 will be returned for my 1. And I only care about the maximum value. Now, I have a different operator that I call argmax. And argmax works almost like max, but it does something different. Argmax will also try to optimize f of x, and it wants to get the maximum value that f can achieve, but it will not return the maximum value of f, but rather the input value that maximized f. Which input value maximizes f? If you know this, send it to the chat. This is 1. That's correct, because for 1, I'm maximizing f of x. So argmax returns the argument or the input value that maximizes f, but not the actual maximum value that f would achieve. So this is a small difference between those two. And we will need this now in order to describe our decision tree learning. So I'm using argmax here. And what I'm trying to do is I have an importance function, and the importance function determines me how important an attribute A, so one of these input variables, is for my examples. So examples is what I have passed here. How to exactly calculate the importance of an attribute is something we will be seeing later, but it's just some procedure to do this. Then, with argmax, I'm going through all the attributes that I have left, because I have this set of attributes. Initially, it's all attributes, but later it will become less and less. So I'm going through all the attributes, and I'm trying with the importance function to determine how important is my attribute for these examples. And what I want to return is not the importance value, but rather the attribute that maximizes the importance function. And the attribute that maximizes this, that's the attribute that is most important. So it could be visible, armed, whatever from before that I want to keep working with. This is super important to understand the difference. So maybe just confirm me with a thumbs up that you understood what this argmax is trying to do. We don't want to find the importance value, but rather the attribute that maximizes the function. And then I'm storing in capital A, which of those, in this case, 3 attributes is the most important one. But I see lots of thumbs up, so that's good. Then I'm building a new decision tree where the root is A. That's fine. We've seen how to build nodes in a tree. Now, this here means I'm going through my values vk in A. So A is an attribute. And this sign here means we're dealing with a set. So what I'm doing is I'm going through all the unique values in the attribute A. Say, if the attribute A would be visible, then unique values would be 0 or 1. If I have enemy distance, the unique values would be less than 10, 10 to 20, or greater than 20. But I'm just dealing here with the attribute from a perspective of a set. I don't care about if a value appears multiple times. I only care about the unique values and I go through them. Then for my first unique value, I'm now doing something like this. And this set operation means I want to keep the elements E in examples. So examples are the training examples. And I want to keep all the ones for which their attribute A, which is the most important one, is that unique value. So for this would mean if enemy visible is my attribute, and I have my unique values 0 and 1, just with this set, and I say my unique value is 0, I just want to keep these values where that attribute is 0. Later, the next unique value is 1, and then I just want to keep that subset, because I say I take all the examples where, so an and, where I also say that their attribute A is my unique value. Now, with this subset, so for example, these examples here, I'm continuing. And in fact, I'm using a recursion. I'm calling the decision tree learning algorithm on my subset of examples, EXS. I have this operation here, and that's a set operation because I said attributes is a set of attributes I have left, but now I have picked capital A as the most important one, and I want to continue the training, but without that attribute. Because my rule is an attribute will only appear at the root, and it will not appear anywhere under it in the subtree anymore, because I've used it for the classification. So I'm taking the set of attributes and I'm removing my most important attributes. Now I'm also using this parameter parent examples, and parent examples were just the examples from before in the last function call. That means just the examples I dealt with here in this function call I'm using now as the parent examples. Then this recursion continues, and eventually it will return me a decision tree. We'll look at the impacts of the recursion very soon, but it will return me a subtree eventually, because we see the decision tree learning algorithm always returns something, either some tree, the most important classification, or not the most important, but say the classification of all the examples left, which would be a leaf then. So I get something back, which I call subtree. And then I'm creating a branch to my tree. So tree is the one I have created here with this root test on A. And I'm creating a branch with this label where the value is my unique value VK. And I'm putting there my subtree. And this iteration I'm running for all the examples, or for all the unique values VK and A. And then this subset here will always be different than in the other iterations. And probably if I have a lot of data that is difficult to separate, I have a lot of recursive calls throughout this algorithm. Through the recursion, I can have these other edge cases. Obviously, at some point, I want to narrow this down to a set of examples where I can just stop, where all the examples, where a subset of examples just has the same classification. So I can stop here. And that's good, or I stop the recursion in this case. There are other cases that can appear because you see, I keep removing attributes in the recursion because I use more and more attributes for building subtrees. And eventually it could happen that I have not finished the training and maybe I have no attributes left. This could be happening. And what I need to do then is I have no attributes left. I'm unable to continue a reasonable training. So I say from all these examples I have left in that recursion, so this will be probably some subset later when this case happens. Then I say, well, I just take the maturity label. I'm unable to fully distinguish this. So I say from all the examples here, I just take that label that appears more often. This is what the plurality value function does. It could also happen that in this case here, but this is a bit of a more special one, but it can happen in the training, that somehow the set of examples I have left could be empty. And if this really happened, then I'm unable to distinguish here further, and I may have to pick the plurality value of the parent examples. That means the examples from the past recursion. But this is a more rare one, but it should be implemented in case this happens. Now, we will now look at a concrete example. We have our data set from here, and I will now go through with you step by step how to learn this decision tree. Do you feel okay for now with this algorithm? So when I explained it, maybe thumbs up if you're okay, maybe thumbs down if there are still some doubts about how it works or if there's any uncertainty. Overall, you look confident. You will see it's actually a bit more tricky than you may expect, because once you have to implement this, it's a little bit of code. The only thing that is left is, before we go through the example, is how do I determine the most important attribute? Somehow I need to do something about it. And before I've said we use something from information theory or from entropy. And this is something I will introduce now. So I've said what plurality value is, and the importance function actually uses entropy theory in order to determine how important an attribute is. We are calculating the information gain. And before we come to the information gain, we need a measure of uncertainty or randomness in a variable. And this is called entropy. Has any of you seen this? I don't know if this is something taught in one of the first semester courses. If you've seen entropy, maybe thumbs up or thumbs down. One has seen it. Maybe you can share with us in the chat where you have seen it. Maybe the cybersecurity students have seen this more often than the others. I don't know which degree program you're from, but maybe let us know in the chat where you have come across this. And the entropy is often called H of some variable, a discrete variable in this case, that can have multiple values and more than two if we wish. We can calculate the entropy. What we look at, what is the we go through all the values, or the k many values in our variable v. Can be 2, can be 3, whatever, as long as it's discrete. We look at what's the probability of this value vk appearing times the binary logarithm of this probability. We have a product of these two values, and then we do this for all the k many values. We sum these products and we put a minus in front. This is the entropy. It can be derived, but this is something you would do in an information theory class. For now, you just bear with me that the equation looks like this. You can also obviously read more about it if you wish, but for us, it's just a helper now in order to determine the importance of an attribute. And the entropy is in a unit that we call bit. But that bit is a different bit than the bits in your traditional computer. It's just a unit called bits for the entropy. And I've heard now from a student here in the chat that this is something you have seen in the introduction to computer science lecture. And there you learned about information theory to determine the information content of a message. We can look at an example now, and I think I'll do this again on the iPad, and we'll calculate this step by step together. So I'll write you down the equation again, that we're on the same page. H of V is the sum for variable k, P of Vk times log 2 of P of Vk, and then put a minus in front. And now imagine we have this example here. We have a fair coin, which is a coin is either heads or tails. And we have a 50% chance that the coin appears on heads or tails. We have another 50% chance. And I want to calculate now the entropy of a fair coin. So I can say the entropy is minus something. So the first concrete value is, say, heads. So P of heads. So this H comes from here, from the example. The H for entropy is obviously a different H. So we say P of H times log 2 of P of H plus P of tails times log 2 P of tails. Now we can plug in these values. We said P of H and P of T is 50%. So we can say 0.5 times log 2 P of H plus, this is 0.5 plus 0.5 times log 2 of 0.5. You're all familiar with logarithms. Eventually, you will get minus log 2 of 0.5. So, because we have 0.5 times this, plus 0.5 times means 1 times this, and then we still have the minus. And this is minus log 2 of 0.5. Remember that this is then minus log 2 of a half. And you know about logarithm rules and how to solve this. Eventually, this will give us one bit. And this means it's actually also the maximum value the entropy can be for this binary variable. And the entropy is actually a measure of randomness or uncertainty. And it's between 0 and 1 for a coin. And if I have a fair coin that I flip, I just cannot predict whether it will be heads or tails, because it's a fair coin, not a loaded coin. That means I just cannot predict it. So maximum randomness, maximum uncertainty. If we change this, say we said heads is 0.8% and tails is 0.2%, then the entropy would be less than 1. It would be more than 0 because there's still some uncertainty. Feel free to plug in the values and calculate this at home or now. We call this a loaded coin because it's manipulated. We could also change this further. We could say heads is 1 and tails is 0. So it will always appear heads. Then the entropy would be 0 bits, because then there is no uncertainty. If I can perfectly predict it will always be heads or always be tails, there's no uncertainty. Then the entropy would be 0. Now you're wondering, what is that useful for? I will now build the information gain measure, and that's a measure to determine uncertainty or to determine the importance of an attribute. So this is the fair coin. There's also a loaded coin that always appear heads. It's 0 bits. Feel free to look it up. And from now on, we will be dealing only with the binary entropy. It's very important, this measure here that we've seen here, we can use this for also variables that have more than 2 possible values, 3, 4, whatever. As long as you know how likely it is to appear, you can calculate the entropy. But we'll only deal with the binary entropy now, because when we motivated decision tree learning, I always said we would care only about trees for labels that are binary. So my prediction will be yes or no, true or false, whatever. And because I need this information gain also to plug in the values of the attributes, or not just the attributes, but also the labels. And the labels are binary. I need the binary entropy. The binary entropy is in this slide sometimes called B for binary entropy, or simply H, but we only use it for binary variables. And if we have the equation before where we said P of something times the log2 of P of something, and eventually it's only binary, that means P of something is value Q, for example, 80% for true. And if I'm 80% true, then I have 20% probability for false. So the inverse is 1 minus Q, because Q is some value between 0 and 1. And the inverse is then 1 minus Q. And then Q and 1 minus Q will add up to 1. So P of Q, or Q, is the probability of the first value in the binary variable, and 1 minus Q is the probability of the other one. And I will need this from now on to determine the probability or the entropy of the goal. The goal is the target or the label I'm trying to predict. And we've seen this before, just going back. We have our 12 examples. And from these 12 examples, we see 5 are true and 7 are false. So 5 out of 12 are true, 7 out of 12 are negative. And one way I can easily calculate this Q then is I say, I take the number of positive ones, which is here 5, and divide it by the number of positive and negative ones. So 5 plus 12. So my Q is calculated by 5 divided by 12. This is Q, and 1 minus Q would be then, for this example, Q would be 5 divided by 12. The other one would be 7 divided by 12. What is this useful for? We can now calculate the entropy, which is a measure of uncertainty of the label value. But that's not enough yet, because so far I have only included the labels, not the concrete attribute values. So I somehow need to plug in now also the attribute, because before we said in importance, I want to determine which one is the most important attribute. And if this only depends on the label, I don't have enough yet. So I also need to calculate a property that we call the remainder. And the remainder looks extremely complex, but I'll discuss this now with you step by step. And then we'll actually apply it to our data set from before. If I have an attribute A, values of A are all the possible values of the attribute. We've seen this also before, like A is a set, it has 2 or 3 or whatever, many possible values. And here it's important that this can be more than binary. We only enforce that the label is binary, but the attribute values can be binary or some other number of values in the set, like 3 or 4 or more. And we have our some attribute A, and then this notation here means the number of distinct values, because values of A gives us all the distinct values in the attribute, which is a set, and I take the number of elements in the set. Can be 2, 3, whatever. And now I want to split my training set E into subsets, E1 up to ED. Remember, D is the number of unique values in my attribute. And I say one of these subsets, EK, so EK is a subset of E, contains all the examples for which the attribute has that value from before. So, for example, the unique value is 0 or 1 or something else. And this notation here means this is the cardinality of that subset, so the number of examples that have this concrete value. I'll show you this again at the example here. Say if I look into attribute A and I look at enemy distance, I have 3 possible values: less than 10, 10 than 20, or greater than 20. And here, if I say, so D would be 3, because I have 3 possible unique values. And if I say, I take the first one, or I take the first subset, where all the entries have the value less than 10, this would be these 2 values and these 2 values. So that would be that subset, E less than 10, for example. And we have 4 of them, and this is the cardinality. And each of these subsets, so each of these 4 subsets, and one subset has these 4 elements, has a certain number of positive and negative examples. I'll show you this again. Here we have these 2 entries with less than 10, and here less than 10. These 2 are positive, one more is positive, and one is negative. This is this false here. Now the remainder is calculated the following. So the remainder of an attribute A is, I'm going through all these unique values in the attribute. So K goes from 1 to D. And I take the cardinality of EK, so how many examples I have in the subset, and divide it by the cardinality of E of all the examples I have left at that stage. And I multiply this with the binary entropy of the positive examples in that subset divided by the sum of the positive examples in that subset and the number of negative examples in the subset. So it's very important when you calculate that this is for this subset EK and not all the examples. This is called the remainder, and the remainder, you're wondering what's the meaning of that? Because if I go along that branch, so I have a subset EK, we need an additional bits of information to answer the question whether to pick that one. And this is described by this binary entropy. And if we randomly choose an example from the training set, that kth value for the attribute with the would have the probability of these 2 cardinalities divided. So if we pick that attribute, the expected entropy remaining after testing on the attribute is the remainder. So if I pick that attribute, the expected entropy remaining would be that. Now we are probably last equation, and then we'll actually plug this in and make it to work. We need the information gain, and the information gain is the measure of importance. Because that's what we always needed, a measure of importance of how important an attribute is. And I'm calculating the binary entropy of my whole example set I have left. That's the uncertainty in the labels we have seen before. And for the attribute A I'm testing, I'm removing the remainder A. And eventually I'm calculating this information gain for all the attributes I have left in my algorithm at that stage. And then I pick the attribute for which I have the largest information gain. So the information gain is just plugged in here. I go through all the attributes I have left, and I calculate the entropy on the labels I have left in examples. And in the information gain, I always subtract the remainder for that concrete attribute I'm looking at. I know lots of equations, but we will now try this out. And I'll show you this on the iPad. So we have three attributes. Well, I'm unable to write on this as it turns out, but that's okay. I have visible, distance, and armed. And I don't know with which of these three attributes I should start. So I need to calculate which of them is the most important attribute. And then I pick the most important one for the root. So let's calculate the information gain for all the data. So D is for now all the 12 examples of the visible attribute. What I need is the entropy of the data set. This is what we've seen before. And then we subtract the remainder. And I'm not writing down the equation of the remainder again. We've just discussed it. If you need to go back to it, just look at it in the slides. But I'll apply it now concretely to this data set. So we have enemy visible. So we have two possible values in visible, 0 and 1. And 6 of those 12 examples have value 0, and 6 examples have value 1. So for 6 out of 12, so these here were these cardinalities from before, from these subsets, because the subset D0, so where the enemy visible is 0, these are 6 of them, 6 out of these 12 examples. And in the remainder, we also said we have this factor and we multiplied with the entropy of this subset D0. 0 is one of the possible values. 1 is the other possible value in visible. And again, we have 6 out of 12 possible examples. So times the entropy of the subset where that variable is 1. H of D is the entropy for the whole data set. We have 12 examples, 5 of them, so entries 1, 7, 8, 9, and 10. So 5 out of 12 entries are positive. So the entropy of 5 divided by 12 minus 6 divided by 12. And now we look at the examples in D0, which are the first 6 examples. And I'm making this a bit interactive, so you can guess or tell me the numbers. Of the first 6 examples, so where visible is 0, how many of them are positive? And how many are negative? We got this right. 1 is positive, 5 are negative, so 1 divided by 6, and 6 divided by 12 of H of D of 1. And from these last 6 examples, 4 out of 6 are positive. Now, calculating these entropies here is something we're not doing step by step. Remember, the entropy equation was here, or the definition of the entropy. So the one case was now, for example, 1 out of 6, then the other case is 5 out of 6, and so forth, or 5 out of 12 and 7 out of 12. I'm not calculating this in detail. Rather, you can use a calculator for this. And in the exam, you're allowed to bring a calculator to calculate these entropies for you. I have calculated them, and you can find them in the slides. So the entropy of 5 out of 12 is 0.98. Then 6 divided by 12 times this entropy, which is 0.65 minus 6 divided by 12. And the entropy of 4 divided by 6 is 0.918. And then we have all these fractions, and the entropy or the information gain is then 0.196. With a calculator, this all goes very smoothly. So now we know the information gain of visible. We also need to look at that for distance. So the information gain for the data set and attribute distance, it's again age of the data set. And now we have 3 possible values in our data set: less than 10, 10 to 20, and greater than 20. And for each of these values, we have 4 examples. So 4 examples are less than 10, for example, 10 to 20, and 4 are greater than 20. So 4 divided by 12 of the entropy where this value is less than 10, minus 4 divided by 12 where the value is 10 to 20, and 4 of the 12 examples were the value is greater than 20. While I keep writing, your task is look at the data set. You have it in the slides and you've just seen it. Find me these 3 values. What is D less than 10? So how many examples of these 4 ones have the value, or no, we have 4 examples where the value is less than 10, and how many of them are positive, or what's the fraction of the positive ones. Look at the data set, maybe don't look at the slides, and I keep writing down the next line already. What's the same is we know 5 out of the 12 total examples are positive, and then I leave this for you, and so you can tell me then what to put in here. Who already knows the first one? So less than 10. I have 4 examples. How many are positive? Someone wrote 3. So the examples I'm looking at are examples 1, 2, 7, and 8. And 3 out of 4 are positive. That's correct. For the examples 10 to 20, these are examples 3, 4, 9, and 10. Who knows how many are positive? 2 out of those 4, yes. And for greater than 20, these are examples 5, 6, 11, and 12. There, all 4 are 0. So here we said 2 out of 4, and here 0 out of 4. And now we can use a calculator to calculate all of this. The entropy of 3/4 is something like approximately 0.811. Very importantly, when you calculate this, always keep this to 2 or 3 decimals, better 3 or 2, not just 1 decimal, because you need to be able to calculate approximate values when you do this on a piece of paper. And if you just use 1 decimal, most likely it will be wrong. There's a small trick. The entropy of 2/4 is the entropy of a half. And this is actually the example of the loaded coin. So this is what maximizes the entropy. So the entropy of 2/4 or 3/6 or 1/2 is always 1, because this maximizes the entropy, while the entropy of 1 or 0, and 0 divided by 4 is 0, is 0. So these are the ends, and the entropy is 0. So this piece here is not further relevant, because the entropy of 0 is 0, or the entropy of 1 is also 0. So we don't need that further. And here we can say minus 4 divided by 12 times 1. So it comes from here. And the entropy, or the information gain, is 0.376. We can do the same procedure for enemy armed. I will not write this out again, but it turns out it's in the slides, and this would be your homework to try calculating the information gain for enemy armed. It's just the same procedure as before. And the information gain for my data and attribute armed is 0.021. So which one maximizes all of this? The information gain for visible is 0.196. For distance, we actually have the largest information gain. That means this is now the root of our tree. And I will say this is our result. We are building it slowly. So distance is the root. And in distance, we have 3 possible values. So we need 3 branches from the root. One branch is the value less than 10. The other one is, say, 10 to 20. And the other one is greater than 20. And now we need to do something for all these 3 possible values. Maybe, because these are now the recursive calls, we split the data set into subsets. So we only look then at the subset where the value is less than 10, 10 than 20, or greater than 20. And we have these recursive calls, and we can see, for example, if we look at our data set where the examples are greater than 20, what do you notice for the examples greater than 20? Always false. So that's actually a leaf. So we can write here false. So here we don't need to do any further training for greater than 20, which is already very good. We can look at that one. We can look at the next one, which is 10 to 20. 10 to 20 are 4 examples, examples 3, 4, 9, and 10. And we see some of them are false, some of them are true. So, yeah, here we don't have a leaf yet. So we need to find out which attribute is the most important one. And the only attributes I have left in that recursion is enemy visible and enemy armed, because distance has been used for the root. So I need to continue the learning. And what I need to calculate is now, I have my data set where I take the examples where distance is less than 10. And I need to calculate the information gain for these examples and the visible attribute, because I don't have a leaf yet. So in here, I can only put visible or armed, one of the other 2 attributes. I'll show you this. We calculate the entropy for the data set where the examples are less than 10. So this is now our subset that we have built, and we are in the recursive call. And from the examples that are less than 10, what we see is for enemy visible, we first of all, for enemy distance less than 10, we have these 4 examples, 1, 2, 7, and 8. And for enemy visible, then in that subset, we have 2 examples left, which are examples 1 and 2, because their enemy distance is less than 10, and we have the unique value enemy visible is 0, and we see one of them is positive and one of them is negative. And where enemy visible is 1, we have our 2 examples, 7 and 8, and we see they are both positive. And we will now plug this into our framework from before, because this here addresses 4 examples, and 2 of them, 2 out of these 4, we saw the enemy distance is less than 10 and enemy visible is 0. So these are 2 out of those 4 examples. So the 4 comes from here, and 2 of them actually are from here. So we have, this addresses 2 examples. And I'm not too happy with the notation. So this should be a subscript. So, and this is a comma, but it's formatted very well in the slides. And then we have we have another 2 examples where the distance is less than 10 and visible is 1. And for those ones here, we just saw this. We saw 1 out of those 2 is positive, and down here, 0 out of 2, or 2 out of 2 are positive, because we saw these are the examples 7 and 8. 2 out of these 2 are positive. So we will plug this now into our framework. So 3 out of those 4 in the subset are positive, minus 2 divided by 4 times h of a half, minus 2 out of 4, because 1 out of these 2 is positive. And here, for the next part, 2 out of 2 are positive. You can use a calculator and you will see the entropy of 3/4 is 0.811 minus 2 divided by 4. And we know that the entropy of a half is 1, so times 1. And the entropy of 2 divided by 2, which is 1, is 0. So minus 2 divided by 4 times 0. And this will actually lead to an information gain that is 0.311. Now we have one attribute left to do the check on, which is armed. And this is the information gain of the data set where the examples are less than 10 and the attribute armed. And if you calculate this, it's also in the slides, you will also see that the information gain is 0.311. Now we have 2 attributes left, but both have the same information gain. What would you be doing then if you have 2 attributes left and none of them is greater than the other? Any suggestions? I don't see any answers in the chat yet. Maybe thumbs up if you think you have an idea what we could be doing here, or thumbs down if you don't have a suggestion what we can be doing here. There's a suggestion to look at the information gain, what it was for the first calculation, so in the recursion before. Yeah, could be done, but we have now picked an attribute, so maybe that will bias the whole decision. In fact, you would randomly pick one of the two attributes, or you could say your rule is you always pick the first one or always the second one or randomly. But here you need to make some choice because you have no more information that you can factor in order to make that decision. So we could be picking then, for example, visible, because we investigated visible first. So we could pick visible. And in visible, we have possible values 0 and 1. And only for the examples that are less than 10. So the examples that are less than 10 are examples 1, 2, 7, and 8. And now enemy visible is 0. We see we have a true or false in examples 1 and 2. But in examples 7 and 8, they are both true. That means we have a new label here. If they are true, then the label is true for all the examples where the distance is less than 10 and they are visible. And for the ones that are not visible, we only have one possible attribute left, which is armed, because there are no other attributes left. And here you need to check based on armed what the label could be. So we look at these top two examples where enemy visible is 0, the distance is less than 10. And if the enemy armed is 0, then we attack, so it's true. If it's 1, we say it's false. So we say 0 and 1. For 0, we said it's a true, and for a 1, it's a false. So we have built more and more of this tree. There is only one part left, and this is the one here, where we said the enemy distance is 10 to 20. So these are examples 3, 4, 9, and 10, and we see the label is not always the same. So I need to do a further decision tree learning here, which I will skip, and I'll show you this in the slides. So in the slides, you find all these values, and they are well written, the numbers. So we calculated these 3 information gains in the beginning for the whole data set for visible, distance, and armed. We skipped armed. I only wrote down the result. Here you see how to calculate it. This is also your practice. We said distance is the root. And then we calculated exactly this for less than 10. We said visible is one of the remaining attributes, or armed. We saw both have the same information gain, so we had to pick one. And then there are 3 or a few calculations left for this one piece that I had visualized, where the distance is 10 to 20, because there we have our attributes visible or armed. And the numbers are in here. It's your homework to try this out. And we see for visible, the information gain is 1. And this is the best possible information gain. So you can stop here. Or if for armed, it's 0. But if you see you have an information gain of 1, you can just stop. You can also stop if the remainder is 0. So, for example, if this was 0.3, but the remainder is 0, then this is the maximum information gain you can get in that recursion. And then you also can just stop, because then if you found an attribute where the remainder is 0, there's no point to continue, because you will not find anything better anymore. And there's a question if this is relevant to the exam, and you see in my Nextcloud past exams, and there is coursework, there are sometimes assignments like this or problems in the exam that you need to learn a small decision tree for a small data set. We can look at this in a moment, because I'll say something about the coursework, and we'll need maybe 5 minutes more or something today. And then we're done with decision tree learning. The whole decision tree, we've almost learned it together, looks like this. For 10 to 20, it turns out that visible is the most important attribute. And then we just have leaves under it. So this is the tree that this algorithm learns. Your coursework is now, we have a small data set that looks something like this. We have a few attributes, and your task is to manually by hand learn a decision tree for finding this label. So the label is here. And you have the attribute, you have 6 attributes: sky, air, humid, wind, water, and forecast, and you have 5 examples. If you have some practice, you can learn the decision tree for something like this by hand in 10 to 15 minutes. And in the exam, you would have enough time to do this, provided you have some practice, and you would also need a calculator to calculate these entropies and deal with the fractions. So, and that's why you're allowed to bring a calculator to the exam. This is something you should be trying on the weekend to get some more practice. And then we have a bigger coursework problem in which you're tasked with implementing the decision tree learning on your own. You're not allowed to use any libraries, but you have to implement this from scratch. And for importance, you implement the information gain. Problem 12.6 turns out to be the exam bonus problem. So if you do problem 12.6, you implement the algorithm and you run it on a data set of your choice and you visualize the tree. This is something you can do alone or in a group of up to 4 students. Then this carries a 10% bonus for the exam. It's important you look at this year's worksheet. If you took this course before, there was a different exam bonus problem, I think. But this year, if you're starting with this course this year, or you have not submitted anything in the past, then the exam bonus problem is this one. If you submitted last year and you have not set the exam yet, then the exam bonus submission from last year still counts. So there's a transition period, but if you have not submitted anything in this course yet, then your exam bonus problem is problem 12.6. Implementing this algorithm will be tough. It will take you a little bit of time, and some things probably don't work the way you expected. So it's good if you find out how to visualize such a tree, but it's a very good practice to better understand the algorithm, plus to work towards a bonus in the exam. And for the exam, sometimes I have data sets like this for which you need to find or learn the tree on your own. But with enough practice, this takes 10 or 15 minutes, and provided you have a calculator. There is a bigger data set here in the slides where I have 12 examples, and the data set is about whether you will wait to enter for a restaurant or not. So a restaurant is full. Are you waiting or not? There's an estimated waiting time. They serve different food. Is it raining or not? What's the price of the restaurant? Are there alternatives around, whatever? And based on these values, you shall determine whether you wait or not. Here, you really only have a sample of all possible values. With our data set before, we had all possible values in that data set. But here it's just a subset of everything possible. So here you really generalize with this data set. If you try to calculate this by hand, this will take you quite a long time, I guess, because there's lots of information gains to be computed. Something like this would not be appearing in the exam, or at least not the whole data set, because it just will never finish. This is a data set you could be using your algorithm for once it's implemented. And once I implemented that algorithm, I don't know, like 10 or 12 years ago or something like this, I ran it and I got a decision tree like this. So this big data set, or not big data set, but say more complex data set, can actually be, you can find a tree, and the tree is relatively small, maybe not the optimal tree, but the ID3 algorithm, as I said, is an approximation, and it's a greedy divide and conquer algorithm. Are there any more questions from your side about all of this? If If you're okay, maybe thumbs up. If you're not okay, thumbs down or send your question. I know this algorithm is complex and it will take you some time to fully understand and implement it. So get enough practice. And it appears quite often in the exam. Obviously, no guarantee that it appears this year, but often it appears in the exams. And it just gives you also, I think, a better practice of trees and how to implement a tree algorithm, because the decision tree learning algorithm we've seen here, it's a recursive tree learning algorithm. It applies divide and conquer in a greedy way. So it's a good revision of a lot of concepts we have done so far, and will definitely give you a better understanding of recursion and trees. Plus, you have learned your first machine learning algorithm. And decision tree learning is, for example, in machine learning libraries like scikit-learn and others available. And here, you at least learn how to implement a very simple decision tree learning algorithm. There are more complex ones, but this is at least something we can do in the introduction to algorithms and data structures. So I will be here still now for an online lab session in case you have any questions about the coursework. And next week, we will only have one online lab session because next week I'm at a conference. And that's why I've informed you about this in iLearn. And today, officially, it's been a lecture-free day, but we're using this to catch up because I'm away next week. And in 2 weeks from now, it's again, because of the holidays, a lecture-free day, but we're doing the same setting, lecture in the morning at 8, and then an online lab session in case there are any questions. So I'm stopping the recording now, and I look forward to your questions in the online lab that is starting right now. And enjoy your weekend in case you're leaving or in case you're watching the recording right now.